Okay, so in this video we're going to look at rotational motion, and before we get into the individual details, let's take an overview of the idea of trying to look at the motion of an object in terms of translational motion, which means along a straight line, compared to a rotational way of thinking about it. I think it would be really helpful if we had a diagram of some object that we could allow to rotate. So let's imagine this is a metal disc that is rotating in the counterclockwise direction, and that we were looking at a small spot on the edge of the disc. Okay, and we're watching this thing move around and around. And we've looked a little bit at circular motion, but we're going to take a look more at the disc itself rather than the thing that might be sitting on this disc. So the thing sitting on the disc is moving around in circular motion, but the disc itself, the entire disc is moving. So there's kind of a concerted motion right there. And so if you can imagine this spot on the disc moving around as the disc rotates, at some later point that spot would be over here. And if you can imagine a line connecting the center of the circle to the point that we're looking at on the disc, you can imagine that line would be sweeping through space as the object rotates. And so there is some angle that has been swept through. And that's a way of speaking about it, and a way of using the angle in a way of describing motion. So, an angle is a fixed thing, in the same way that a displacement is a fixed thing. But if you allow that displacement to change, or you allow that angle to move, then you get motion. And when you think about the motion in an angular sense, the word that you're going to hear them use is that it swept through a certain angle. So it might have swept through 50 or 100 degrees, or in this case, we're going to use radians. As it sweeps through, as that imaginary line connecting the center to the point in question, as that line sweeps through space, carving out some angle, there's also moving that point through some distance. And we really want to make a connection between that. If you have explored or studied the unit circle, then a lot of what you've learned in the unit circle is kind of underlying this idea. So that distance can be called x, or in some cases it's called s. Part of the reason for using the letter s is x you might tend to think of as moving again along a straight line, but in this case obviously we can't go around a circle moving in a straight line, so s is typically the letter that you would use. It's a little more generic than the letter x. It could represent any kind of path. It doesn't necessarily have to be a straight path, and it's particularly useful when you're talking about things like an arc length. So some length along a portion of a circle, not the entire circumference of the circle, but just some portion of that circle. And when you measure the angle in radians, that is just a natural way of speaking about circles that is sort of natural to their geometry. So we'll talk a little bit more about that when we get into the details of each of the different areas that we're going to explore. But ultimately, there's an equation that is kind of underlying that unit circle, and that is that the distance around any circle, and this would be true not just of the unit circle, but of any circle, would be equal to the radius of that circle multiplied by the angle that was swept through by the object as it moved around in the circle. If it doesn't go around in a complete circle, no problem. You just need to measure the angle, but that angle needs to be measured in radians. So let's take a look at the different properties, and we'll come back to this as we work through them. The lowest level of motion, it doesn't even require you to have motion. I mean, you have a displacement all the time, but if you change that displacement, then you do get some kind of motion, and that typically would be represented by x or by delta x. Okay, the equivalent property in rotational motion is not a distance in meters, but an angle that was swept through. So that is the most important angle. And the symbol that we're going to use is theta, but there's lots of symbols you can use for the angle. Phi is another one that's very common used. You can use letters like A, B, C are also very common, capital letters. And we can actually connect these two together by using this equation, right? So in this particular example, the x is the distance along this path, and that would be equal to the radius of the circle times the angle, so long as that angle was in radians. Okay, and let's move our way up through the different levels of motion. So after displacement, once something has been displaced during some period of time, that would mean that the object had velocity at some point. We typically use the letter v. The name for this guy should be pretty easy to understand. It's called the angular velocity. It has the symbol omega, which is kind of a curly W, like the letter W, but if you can curl the top portion in just a little bit. And then the relation between those two is that v, the velocity in a translational sense, would be equal to r times the angular velocity. And this, just so that you know, this is occasionally referred to, I should say, as the angular frequency because of the units for it. And we'll get into that more as we get a little bit deeper into the topic. But again, velocity has its angular counterpart called angular velocity. The next level of motion would be acceleration. So if we allow the velocity to now change, then we would experience acceleration. That uses the letter A in the translational motion. On the rotational motion side, as you might guess, it is just simply called angular acceleration. It also uses the letter A, but it uses the Greek letter A. And so probably no big surprise that the way that you would translate from rotational motion to translational motion is you would just multiply R times, in this case, alpha, and you would get the linear acceleration. Okay, so those are the three properties that we looked at for kinematics. It is possible to have a changing acceleration. We don't really have a special name for that. So the next step then is to start moving to some of the other physical principles. So rather than just the definitions of motion, let's take a look at what causes those motions. And in order to do that, we have to just introduce one property, which is used in all of the calculations that we're going to be looking at coming up, and that is the mass of the object. We use the letter m typically. Now here's the problem with rotational motion, and we'll talk about it a little bit more when we get into torque. It does matter the mass. I mean, of course, for translational motion, the more mass you have, the more difficult it is to move you. And the same is true for rotational motion, but it's not just the mass of the object. A heavier object would be more difficult to rotate, but also it depends on how that heavy object is distributed. So, for example, the name for this property is the moment of inertia. It uses the symbol I, and the way you calculate the moment of inertia is that it's almost like you have to take the disk that we were looking at here, or the object, whatever the object is that's spinning or rotating, and you need to break it up into smaller pieces. And we need to take the mass of that piece and then multiply it by how far it is from the radius, from the center of the motion squared. So each little piece of the disk has its own moment of inertia. And if we want to know the moment of inertia of the entire disk, well, then we would have to add up all the moments of inertia of all of the different objects that were there. So we would take the mass of the object and multiply it by the square of the distance to the center of the object. Now, obviously, that would be a really tedious process, and we're not ever going to do that in this class. But what we will do is look at derived formulas for certain shapes. So like, for example, a cylinder or a sphere, there are established equations that will allow you to calculate the moment of inertia without having to go through this really tedious process. But essentially underlying that process is this idea that you're simply calculating the moment of inertia of each individual piece, and then you're just going to add them all together. The symbol for sum, or you might also think of total, or even like net. The net moment of inertia would be another way of describing this. Okay, so once we add mass to the mix, now we can start looking at the three big properties. So those would be force, momentum, and energy. So let's start first with force. Obviously, force uses the symbol F. The equivalent property in a rotational sense is called torque. It uses the Greek symbol for tau. It's kind of a wavy line with a little lowercase t connected to it. This is the last one where we're going to be able to connect. I can calculate the force from the torque, or the torque can be calculated from the force. And the way that you do that is the formula for torque is F. So in a rotational sense, yes, the force matters. Of course, it matters how much force you apply. But what also matters is how far away do you apply that force from the point at the center of the rotation. And then the last thing that makes a difference is the angle. So it turns out that if you don't apply the force at the right angle, then you don't get as much torque as you could. And so we'll explore this equation in a little bit more detail. But whenever you hear the word torque, for a rotational sense, you should think the same thing that you think when you're thinking about translational motion, or you're thinking about linear motion. You think about how forces make objects speed up or slow down. Torque does the same thing, except that instead of speeding up in a linear sense, it speeds up in a rotational sense, or slows down in a rotational sense. Or perhaps it even moves at a constant rotational, at a constant angular velocity with no angular acceleration at all. Now, force, actually, there are several ways that we could look at the force. So let me just put a little extra word on here. When we want to know the net force, so that is to say the total of the force, I could use the summation symbol that I used right here. I could use right here, the sum of the forces. Well, then we need to look at the equation for force, and that is that F is equal to ma, or F net is equal to ma. Now on the other side, we would have the same thing, the net torque, except that in that case, the net torque, or actually let me write it this way, the net torque is equal to, okay, now we need to translate. So the property that would be the equivalent of mass in a rotational sense would be I, and for acceleration that would be alpha. So the formula for torque in a purely rotational sense, not trying to connect it to the force that's acting on the object, but in a purely rotational sense is the torque is equal to the moment of inertia times the angular acceleration, the same way that the net force is equal to the mass times the acceleration. Now there's an alternate way that you could do it, and that is that we could say that F net is equal to delta P over delta T. So if I break up the A into delta V over delta T, then I would end up with the change in momentum divided by the time, and I can get a similar equation over here. Okay, now we haven't talked about this yet, but the symbol for angular momentum is L, and then the time portion we don't need to change at all, because again, time is not a property that has anything to do with rotational motion necessarily. It's just simply a property that both rotational and translational motion, it's a way that their motions are measured against the time. Okay, so let's look at the other areas of physics that we have talked about. So let's take care of momentum right now. The symbol for momentum is little p is equal to m times v. There is something called angular momentum. The symbol for that is capital L. And then again, all we need to do is to translate the translational motion into the equivalent properties in angular or in rotational motion. So the equivalent property for m is I, and the equivalent property for velocity would be angular velocity. So that is going to be omega. Okay, that just leaves one last property to take a look at, and that is in the area of energy. So we're not going to look at every form of energy, but let's particularly take a look at kinetic energy, because that's obviously one that's going to be present in any spinning object. There must be some energy associated with that motion, but it's not translational motion. So then we have to have some way of thinking about how to calculate that. So the formula for kinetic energy is 1/2 mv squared. So there is something called angular kinetic energy. Its symbol is actually still just EK. So this is one of the few symbols where we are going to change it. It's energy is energy. Doesn't really matter whether it's angular or otherwise. Energy is energy. But we do need to translate the formula. So 1/2, the equivalent of m is I, and the equivalent of v would be omega squared. Okay, and really important thing to recognize, all of these properties produce the same units. So the force will come out to be in newtons, the momentums will come out to be in kilogram meters per second squared, or kilogram meters per second, and then in kinetic energy it'll come out to be joules. And that would be true even if we were to calculate the work. So when I write the equation for work, I'm going to try to be really careful to make my W very angular, very straight line, so that I don't confuse it with omega, because now we're using those two symbols. Oftentimes they may be used together. So in this case, the work is equal to force times displacement. The work here, you don't even need you don't even need to put the word angular on it, but you certainly could. It wouldn't be wrong to do it. So that symbol for angular work. So if we look at the two properties, the equivalent property to force, again, is called torque, and the equivalent property to displacement would be the angle. So I would take the torque and multiply it by the angle through which it turned, and I would end up with units of energy. That would be units of joules. So all of these properties have equivalents in both the translation and the rotational world, and we're going to go through in the upcoming videos, and we're going to look at each one of them individually, and practice solving problems looking at rotational motion. It's not a huge it's not a huge amount of information to add. It's really just these first three properties. So really being able to visualize what the meaning of the angle theta, the angular velocity, and the angular acceleration, and the rest of the stuff will kind of fall into place.